Hello students, and welcome to section 6-3, exponential growth and decay. So we're going to be taking a look at, as we jump in, and the explore and reason portion again, please take a look at on your own. We will be able to apply problems like this later in context once we complete the lesson. So example 1, exponential growth. The population of Hillville grows at an annual rate of 15%. What will the estimated population of Hillville be in 5 years? Okay, so let's go ahead and take a look. You, as you know, can model exponential growth with a function. Here's our Hillville sign, population 5,000. But you can model exponential growth with a function f of x equals a times b to the x, where a is greater than 0 and b is greater than 1. As it turns out, we can also attribute that b, or base, using this quantity 1 plus r. An exponential growth function has a growth factor that is equal to 1 plus the growth rate. Step 1. Write the exponential growth function that models the expected population growth. Let x equal the time in years, a equal the initial amount, and r the growth rate. So again, using this equation, f of x equals a times the quantity 1 plus r to the x power. We know the population is 5,000. We know the rate of growth is 15%. As a decimal, 0.15 will be what we use. And then, of course, everything else is as is in the equation. We do the math, and in a little bit we'll see the final answer, or at least the equation, but 0.15 plus 1 yields 1.15. So you've got that, and then the function, of course, ends up looking something like this. The function f of x equals 5,000 times the quantity 1.15 to the x represents the exponential growth model for this particular population. Continuing on. Step 2, find the expected population in 5 years. So now that we have our model, look at the next step. We can plug in or substitute 5 in for x. So f of 5 equals 5,000 times 1.15 to the 5th power. And that analysis, if you do this on your calculator, ends up being 10,056.79. In 5 years, we'll round it up, though, to an expected population about 10,057 people. There is a try-it problem that you can take a look at later on your own if you'd like, as usual. Let's take a look at some of the concepts here. Interest in particular. Interest is calculated in 2 ways. There's simple interest and there's compound interest. Simple interest is interest paid only on the principal. Compound interest is interest paid both on the principal and on the interest that has already been paid. The compound interest formula is an exponential growth function. Simple interest is just a linear function. So here's our equation or formula. A for amount paid is equal to P, the principal amount, times the quantity 1 plus R, rate of interest, divided by N, number of years per, or number of times per year the interest is compounded, and then that's all raised to the NT power. Again, N, same value, but T now is the time in years. So the graph below shows $10 at 5% simple interest and at 5% interest compounded quarterly. So the red line you can see, and it is just a line, is where if you start with $10 over the course of time, your money is growing, but it's only growing linearly. The R value is the same. The equation for the simple interest expression is just I equals P R T. I being interest, P being principal, R rate, T time. And then once you find that I value, knowing those 3 values, P, R, and T, you can essentially add it to the prior number. So at 0, 10, that's 1 point. and so on and so forth. You have 10 years at another, and then continue on. This line progresses as you probably would expect a line with a positive slope to progress over the course of time. However, look at the blue curve. The blue curve, this is an exponential growth function, and that most certainly is growing at a much faster rate. Okay, instead of having your money here after 20 plus years, your money's up here. Let's say instead of $10, it was $10,000. You're not just looking at a growth from, roughly 20,000 starting from 10, but you're closer to 30,000, if not higher than that, starting from 10. So it's much better to have your money grow at an exponential rate than it is certainly than a linear rate. So if we move on, example 2, we're going to go ahead and take a look at exponential models of growth. Kimberly's family invested in a certificate of deposit, a CD, for her when she was born. The interest is compounded quarterly. What is the value of the CD at the end of 5 years? So it says use the compound interest formula, which is right here. Okay, I'm going to go ahead and move this as well. There is the CD, we say. The amount deposited is $3,000. The annual rate or interest rate is 8%. It's compounded quarterly, which, by the way, if T is the time in years, quarterly would be, if you think about it, there's 12 months in a year, so that would be every 3 months. So every 3 months you have 1 quarter. Therefore, of course, 3 times 4 ends up being 12. All right, so here's the setup. I think we can stick to maybe this first. Go back to that. A, again, equals P times the quantity 1 plus R over N to the NT power. The numbers that make sense here to substitute in for variables, 3,000 was the principal, 0.08, 8% as a percent, but 0.08 as a decimal is the R value. Like I said earlier, N equals 4 is the value we use. Technically it's 3 months, but 4 is the N value that represents the quarterly kind of breakdown of things. But every 3 months represents a quarter. The principal amount is 3,000 as it says, the rate is 8%, 0.08, and then the number of times per year, like I said, the N value there would be 4. So the next step, the analysis continues, just divide. It also says, where on the next step you see the calculation continue, but it also says the 8% interest is paid over 4 periods. So 2% interest is paid each period. All right, that's an interesting kind of setup from this to that. If you just left it as this, you can see that it's clearly quarterly, but they're describing this, noting the 2% interest paid each period as opposed to 8%. Again, it's just a matter of the calculation leading to that. Use this equation as your primary kind of focal point when you start. Continuing on, again, you see this take shape because you can add those two. Plugging in 5 for T because this is being done over the course of 5 years. So what's the value after 5 years? Do the math. So the $3,000 investment ended up being $4,457.84. Pretty nice after 5 years to look at your return of investment, they say. Will the value of Kimberly's CD be greater after 15 years if it is compounded annually rather than quarterly? So we haven't yet discussed annual compounding, but annually pretty simply means you're going to do that once per year. And your money hopefully will grow, well, you would hope it would grow better or more, but we'll see. Quarterly is actually more times per year versus just once per year. Compare the exponential function you found in Part A with the annual compounding, n equals 1 over the same 15 years. Quarterly and annually, here we go. We can see here that we already, if you recall, ended up with that setup with the values plugged in accordingly. Here, on the right side, we're only going to be plugging in 1 for n. So everything else is the same. It's still 3,000. It's still 15. And yes, we did, or they did modify this from 5 to 15. That's a quick and easy way to do the analysis, of course, but it's technically the case in this part B. Part A was 5 years, this is 15, right? So again, here's the changes. We've got the same rate, different N, same time, different N. So what happens? Look at the two equations there. Clearly the base here is bigger than that base there, but look at the exponent. This is 60 versus 15. Look at the difference. So you're actually going to have more money, $9,843.09 quarterly compounded versus annually compounded, 516, 0.51 or 51 cents. The value of Kimberly's CD will be less if the interest is compounded annually rather than quarterly. So always choose more compoundings because the end value will increase accordingly. And then, of course, you'll have more money. So that's a great example of how best to invest. Example 3, exponential decay. A video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases by 25% each day after that. In how many days total will the video stop being a fan favorite? So let's take a look. There's your function. Okay. 0, there's a number of views. 1, and so on. The number of days and then the number of views, as you can see. So 0, 8,192, and then after that we're looking at a decrease of 25%. Okay? So we can model this. All right, we've talked about exponential growth, but let's now talk about exponential decay. You can model exponential decay with a function of the form, again, y or f of x, same thing, equals a times b to the x, where a is greater than 0, but b is between 0 and 1. You can see the equation again reflected here. This is different now because, well, we're not adding, we're subtracting the r value. Everything else is the same. The decay factor is 1 minus the decay rate. And you can see that right here. So 1 minus the r represents, as again, r is the decay rate, but that represents what we call the decay factor, as opposed to the growth factor when we did growth functions. Okay, step 1, model the situation. X is the time in years, A is the initial, R is the decay rate. Here's your generic or general form for the decay function model. Plugging in 8,192. Plugging in 0.25, again for the rate, it's going down 25%. And then we do the math, as you can see. So 8,192 times 0.75 raised to the x. The decay factor, it says, is written as a decimal less than 1, not surprisingly. So when you do that, step 2, it says, write an equation to find x if f of x is 1,000. We're going to substitute y, or f of x, excuse me, same thing, with 1,000. Using this exact same formula, and we're going to go from there. Estimate the solution of the equation using a graphing calculator. On your graphing calculator, you can type in the function, and as you can see here, there's a table feature. If you hit the upper right corner of your screen, you hit second graph, you can see the table of values. These table of values is a representation of something I've done in the past. But once you type in your function in y1, don't mind these two functions. Once you type it into y1, you'll be able to do your analysis from there. But look, at 8, you're at about 820.12. So use the table feature, and then again, finding the value of x when y is less than 1,000. Well, that's the assessment. So the video will stop being a fan favorite after 8 days. Example 4, I'm going to go ahead and ask that you take a look at this on your own, as well as example 5. And we'll be able to touch base on this our next live day. So please take a look at example 4 and 5 again on your own. The completed notes are below this particular page on OneNote.